o'clock. So if I could ask everybody who hasn't a seat to take a seat, we can sort of get started with our next part of the program. So I want to welcome everybody to the Create Mini Conference 2016. This is actually our 5th mini conference. And I have to, I myself was impressed as I looked at the audience and looked at all the poster about how strong it's still going after 5 years. I was actually even more deeply impressed when I looked at the quality and the variety of papers K through 16, posters K through 16. I think we should feel really good that at one university we can actually produce the quality of work to really try to figure out how to improve the teaching and learning of science, math, and engineering at one university. You should really feel good about yourselves. I think you should give yourself a big clap. And the level of conversation I thought also was extremely powerful. I don't know how many of you go to poster sessions at different conferences, but I thought the quality, the level of conversation was quite impressive. I have one extremely important announcement that I have to make. Someone lost a cell phone. So if you don't have your cell phone, Sue Carpenter has her cell phone. So feel good about it. She has it. Don't worry about it. There she is. We got it. Good. So I wanted to make sure I got that done. The second thing I really want to do is thank 3 people. There's a lot of people that actually were responsible for today. You don't get an event happening without a lot of effort. And there's 3 people that were particularly important for allowing this to happen. One was Chris over there with the camera. He's really not a photographer, but he has he wears many hats and create for STEM. So Chris was certainly really important. Sue, that many of you know, was certainly instrumental in working with Chris. And then you guys seen this person running around on the little electronic thing? I guess he turned off. No, Zach Nussbaum, who worked for Crate for several years, moved to Arizona, but he still stays involved with us. And Chris actually was able to do lots and lots of work from Arizona to help get this conference, this little mini conference together. So I really want to thank Chris, Zach, and Sue for their work in the mini conference. And so with that, I'm going to it's my pleasure to introduce Jim Pellegrino. I've known Jim for a number of years. We go back until a lot of exciting things started happening in the late 1990s, early 2000s about the use of technology and really exploring learning and what does it really mean to learn. So I've known Jim for many years. He's been a good friend, a good colleague, and a good mentor. So I'm really pleased that Jim actually accepted our contribution, our invitation to come and actually present to us. Jim, I think, as many of you know, is probably one of the leading experts, not just in the United States regarding assessments, but throughout the globe. Jim is asked to speak all over about his thoughts on what does it really mean to assess kids and how do we assess kids. So it's really quite an honor that Jim accepted our invitation to come and speak to us, and I'm sure that many of you benefited tremendously from Jim's interactions at the poster sessions and some of the talks that you guys had with Jim. So it's with that, I have also some announcements. I forgot. You have to get the other announcements. Sorry, not yet, Jim. The announcement is that we only had half our posters. So we saw half of our posters that were at this first session. After Jim's talk, we're going to have the second half. So please stick around for the second half of the posters. People will certainly be around talking. Jim will still be hanging out, and you can talk to Jim. But the other thing that I want to encourage you about it, there'll be lots of pictures and stuff about the session up on the Create website. So go please check out the Create website after this. And so with that, I'm going to ask Jim to come up and he can plan his talk. So let's give Jim a big welcoming for being with us. Thank you, Joe, but I got to figure out how to turn this on. I think I just did. Thank you. Well, first of all, thank you for the introduction, but it's also a pleasure always to be back at MSU. There's several folks here that I've known over the years, and also, as Joe did mention, we're involved in collaborative research projects, one of which I'll talk a little bit about today. And so there's several people here that
that I enjoy interacting with. If not physically, we have our regular Zoom meetings, and so I feel like I'm always a part of MSU and in touch with folks. I also want to make a comment about the posters and everything. This is really, really impressive. For somebody coming from outside to see so many different projects where folks are trying to grapple with hard issues in STEM education. And I look forward to the rest of the posters. So I'm very delighted to be here and try to share with you some thoughts today about what is, I think, probably the most challenging thing that might be facing us right now, which is how do we start thinking about this brave new world of what we want in STEM education and outcomes of STEM education. I start with this. I actually used this to for an article I wrote a couple of years ago because there's this idea of a Chinese curse. May we live in interesting times, I think we are living in very interesting times. Of course, it turns out there's no such thing as Chinese curse. This is a Western invention. And when Kennedy made this pronouncement or made this point, it was a very different world. But I think it applies very aptly to where we are in science education because these are very interesting times. They're times of danger and uncertainty because there's an opportunity that exists for us to dramatically change the nature of science education across the spectrum. But the times are very challenging in terms of how do we capitalize on this, and maybe I should put it in a more crass form, how do we not screw it up? What is it that makes it such an opportune time? Well, one thing I want to note is that I think there's really components for vision and change across K-16. So one of the things, and if we can think about three things, and there's more than that. First of all, we have the NRC Science Education Framework and the Next Generation Science Standards. Many of you are familiar with that, but that essentially lays out a fundamentally different vision for what we want to have happen in K-12 science education. The second part of this, and sort of happening in parallel, and in some cases antecedent to the NRC K-12 Science Education Framework, was the redesign by the College Board of AP curriculum frameworks and exams for biology, chemistry, and now physics. And that's been underway for a while, and I'll mention more about that in a little bit. And then the third thing is, in addition to all the things that I've noticed on posters about things happening in higher education with respect to disciplinary units, I want to mention in particular the AAMC's efforts to define a competency framework for entry to medical school, as well as for the redesign of the MCAT in 2015. And I'm not sure how many people are aware of the dramatic shift in the expectations about what students are supposed to know and be able to do with science with respect to the MCAT. So these three things together almost sort of constitute some reasonably consistent and coherent components of a vision for science education, and in particular change in how we educate students as we go forward from kindergarten all the way into medical school. Now, to me, the clearest sort of definition of competence is the one that has come from the work of the NRC framework, which, as many of you know, has proposed that competence is composed of three dimensions, one of which is disciplinary core ideas, the other is science and engineering practice, and the third is cross-cutting concepts. And in defining those three dimensions that contribute to competence and proficiency in science, they went a step further, and the point that was really important was the idea that it's not just about each dimension, it's the integration of those dimensions into what are called performance expectations that represent the intersection of the three. And that this intersection, the blending, the combining of cross-cutting concepts, disciplinary core ideas, and science and engineering practices is really the kind of attainment that we seek for science education, and that's true whether we're talking K-12. It's also true, I would argue, for things like AP, and it's also true now with respect to things like in higher education. The NRC also, I think, framework also articulated this idea that competence is something that develops over time and increases in sophistication and power as the product of coherent curriculum and instruction. I think many people in this room know that one of the ways we would have to characterize K-12 science education, as we have known it before, is not exactly coherent integrated curriculum instruction. Very, very spotty, very kit-based, a unit here, a unit there, but not something where the idea is that students develop understandings that become increasingly sophisticated and powerful over time. So we're talking about a progression, but that progression is not just is the product of a coherent program of curriculum and instruction. So it puts a burden on things with respect to that. And it lays out goals for teaching and learning, as many of us know, which is the idea that students would engage in coherent investigations of disciplinary core ideas over multiple years of schooling. They would be blended with the science and engineering practices, and that the way in which we express this is through these performance expectations that require students to demonstrate understanding demonstrate that they can reason with these core disciplinary ideas. And how do we do that? We express it in terms of what I call verbs of cognition that explicitly identify the kinds of things we want students to be able to do that relate to demonstrating your understanding. Explain, predict, model, justify, argue, and that it is at this level of specification that we get a clearer sense of okay, what are we trying to get kids to be able to do? And that's going to cause us nightmares now as we try to think about how do we know that they can do that, which is the assessment problem I'll get to in a little bit. You can't read that because it's you could probably read parts of it, but this comes from an NRC report in 2015, which I think is a very nice depiction. On the left it says science education will involve less, and on the right it says science education will involve more. This is a part of it, and I think this contrast sets up very nicely what the shift is. Moving away from rote memorization of facts to facts being learned while developing explanations and designing solutions supported by evidence-based arguments and reasoning. Teachers providing information to the whole class versus students conducting investigations, solving problems, and engaging in discussions with the guidance of teachers. So this sets up a very big frame for the shift that we want to have happen in classrooms in terms of how are we going to get students to develop this integrated three-dimensional understanding that brings together disciplinary core ideas, science and engineering practices, and cross-cutting concepts. It means a complete shift in the nature of the discourse practices of what's happening in classrooms and how students are transacting with each other and with their teachers the mastery of ideas and concepts and arguments. Of course, it helps us also understand and start to think about if this is the sort of what we're trying to do in terms of how we're trying to change the nature of instruction, where does assessment fit in this? What is assessment? So assessment is one part of the picture in sort of helping move this agenda forward. And some might think it is the most important part. I would argue that it is one sort of part of three three elements that in all of education we have to sort of coordinate. And those things are curriculum, usually identified by things like standards, instruction, what it is that teachers and students do to master those elements of the curriculum, and assessment, which is how is it that anybody's going to know, students or teachers, whether they are making progress in attaining those standards. And one of the things we know historically is that the extent to which these three things are aligned with each other is oftentimes problematic. And one of the reasons why it's problematic is because assessment, if we don't conceptualize it properly, can skew the entire process. Teachers can spend their time focusing instruction on what's on the test or the assessments, and that leads to a limiting of what is in the curriculum. So what many people have argued is the assessments oftentimes are a negative driver in the sense they narrow the curriculum relative to the intended outcomes. So that's one of the things we have to think about when we talk about assessment as being a part of this whole picture of transformation, whether it's the large-scale assessments that the states are going to use as part of monitoring progress towards achieving science proficiency, or the assessments that teachers are going to use in classroom. Some of us also argue that this coherence among curriculum instruction and assessment can only be achieved if the three things are connected to the same underlying conceptualization of what it means to know and learn. Okay, and this is what comes from research. It comes from translation of research into things like standards. But the point is that there has to be some way for the assessment to align, the assessment, the instruction, and the curriculum to align with each other. And rather than trying to align them separately, if each of those three things is aligned with the conceptualization of what it means to know, what's important to know, then we have a fighting chance of having better alignment. And so assessment is just one part of the picture, but it is a key part, and it needs to coordinate with the other two. Assessment is also not an easy thing to do well. When we did the report, Knowing What Students Know, I mean, one of the things that we argued is that assessing student knowledge and understanding is a far more difficult problem than measurement in the physical sciences. We don't have tools like you have in the physical sciences. We don't have a yardstick. We don't have a measuring stick or we don't have something that can measure certain quantities. And my metaphor, as I'll use Bob in session, if I want to know how much he knows in a particular area of STEM, I don't have the equivalent of a dipstick. I can't go in and pull it out. He's up a court. Joe would be dead. No. So we have to understand that this issue of designing assessment. Is it the mic or is it me?
Yeah, so we're going to switch it.
You got your back.
The dipstick.
All right. Is that any better?
Yeah.
Okay. So we have to recognize that assessment is fundamentally a process of reasoning from evidence.
It's fine. It's much better.
Okay. I can't tell from the feedback. What do I mean by that? That what we're doing when we're assessing student understanding, student knowledge, student competence, is we're engaged in a process of reasoning from evidence. And for that process to work well, it has to involve three elements that have to be coordinated with each other. And the first thing that drives this is the idea of cognition. All assessment should emanate from some conceptualization, whether it's theories, models, and data on how it is that students represent knowledge and develop competence in some domain. Because the way in which we conceptualize what it means to know and what it means to learn is the key driver in then what we do, which is the observation part of this assessment triangle, which is essentially the thing we have control over. And the thing that we can do is ask kids to do something. Write something, say something, draw something, sing something, dance something, whatever it is. But those performances, that is our source of evidence. And what we ask kids to do should be driven by the conception we have of what is important what is important knowledge that we want to try to get a window into and make manifest. Because the conception we have of what that means to know should drive us to sort of figure out the kinds of performances we want them to take on and the kinds of evidence we need to see. And of course, the third part of this, in order for this to work, is we have to have a method or to a way of interpreting or making sense of that evidence back to the inferences we want to draw. So assessment, I used to, sort of my favorite joke is when we had the NRC committee that did the Knowing What Students Know report, we essentially took 3 years, we had 16 people, a lot of money from the NSF, didn't go to any of us, and went to the NRC, and the best we could come up with is a triangle. But the triangle is a very important and representation of the fact that assessment is really a process of reasoning from evidence. And these three things have to be coordinated, because if they're not, then essentially it doesn't matter how elaborate our theories of knowing and learning are. If we have inadequate observations, we cannot draw inferences relative to the kind of knowledge that we're interested in. On the other hand, if we have very elaborate theories and very elaborate performances, but we have no way to make sense of the evidence relative to the inferences we want to make for the intended use, that doesn't accomplish anything either. So we have to understand that assessment is really an interesting challenge, even in the simplest case, and it's now made that much more difficult, I believe, in the context of the idea of integrated performances. So there's at least three grand challenges that I think we can lay out for ourselves with respect to science assessment. One is this idea of designing valid and reliable assessments that reflect the integration of practices, cross-cutting concepts, and core ideas. To be blunt, we've never really done this at any scale, whether it's at the classroom level or at the large-scale level. And so there's a large problem of design and validation that has to engage us. This is not a simple problem. It's going to take us a while to work this through, which has a variety of practice and policy implications. The other thing is that we need good assessments because we need to use these assessment results to establish empirical evidence regarding progressions in science proficiency across K-12. Because many of the progressions that are included in the framework in NGSS are based on relatively thin sources of evidence, or none whatsoever. They're hypotheses. And assessment can actually be a key thing in informing us about what those progressions look like and validating them and actually allowing us to build essentially better curriculum materials, instructional practices, and update the standards whenever that's going to happen the next time around. The third thing is that we need to build and test tools and information systems that are going to help teachers effectively use assessments to promote learning in the classroom. And I emphasize the fact that it isn't just about building large-scale assessments. It's really about building things that can help teachers and students attain the vision for science learning and science proficiency that's embedded in the framework and the standards. So we have a series of challenges, and one question I want to explore is where do we stand in meeting these challenges? And I want to argue that because of the last decade or more of research and development and various projects, two of which I'll talk about, we do have increased awareness now of what it means to, what the development of confidence should mean and the possible implications for designing coherent science education. We're nowhere near where we ultimately need to be, but it's not like we're starting from scratch and we haven't figured out some key things along the way. I would argue, and I'm going to give you two examples, that we have examples of thinking through in detail this juxtaposition of disciplinary core ideas with engineering, with disciplinary core ideas with science and engineering practices to guide the design and integration of curriculum, instruction, and assessment. And I'm going to refer to two projects. One is the AP Science Redesign, and then the other is the project Joe and I and others here are working on. I'll briefly touch on that, which is designing assessments for middle school physical and life science. So let me start with the AP project. Some of you may know that in 2002, the NRC issued a report which was actually a fairly scathing critique of advanced study in mathematics and science in the United States, AP and IB. And there were a variety of things that the report recommended that needed to happen, and some of them are mentioned there. The NSF and the College Board engaged in a project that began actually in 2006 to take on the challenge of redesigning AP Science. I had the privilege of working on that with one of your former colleagues here. Mark Ricase was co-PI with me and Gene Pemberton, a chemist, on the AP Redesign project. And what we tried to do, starting in 2006, was to draw upon a variety of resources, some of which are up there, to try to think through what would it mean to not just build a better AP exam, but to build a better AP in biology, chemistry, and physics. And I'm going to sort of give you a tour through that if you're not familiar with it. And just to give you an idea of how long it takes for certain things to change, this is the timeline for the AP redesign. And I want you to, this is too small for you to read. We started in 2006. In 2015, we're still not quite finished with the AP redesign. Some of you may know that the first course that was redesigned, the first new AP biology exam was in 2013, AP chemistry was in 2014, and AP physics was in 2015. So it takes quite a while to try to think through and work through some of the details of what it takes to redesign something that is as high stakes for students and other stakeholders as something like AP. And the way we did it was to use evidence-centered, we used two things, backwards design and evidence-centered design. And I want to talk about this in terms of three critical design phases that help explain how you get from ground zero to integrated curriculum instruction and assessment. So the first thing that we talk about is what we call a domain analysis. Domain analysis is really bringing together domain experts and asking them a very fundamental question. And not an easy question for domain experts to answer is what's really important in your domain or discipline for students to know and understand. And the first thing you have to do when you bring domain experts together is to tell them, put away your textbook. Okay? You can't pull out the textbook and take the topic list. You have to think about what the domain is. So basically what we asked the domain experts to do, biology, chemistry, and physics, was to think about you might sort of say, the content side of this in terms of big ideas, enduring understandings, and supporting understandings, and develop a representation of that important disciplinary knowledge. At the same time, we ask disciplinary experts and learning scientists to describe a set of science practices that go along with that disciplinary content. So it was actually in the AP redesign, starting in 2006, that this idea of disciplinary content knowledge, core ideas, and science practices first took its expression in terms of thinking about the redesign of the AP course to develop a domain model that essentially allowed the disciplinary experts to begin to express what is important to know in science in terms of both the content side and the practices side. Of course, everything we did was peer-reviewed. This is exactly how it felt. Because you had to have acceptance by disciplinary experts. No matter how good the groups are you assembled, you still have to it has to be credible with the field. And for those of you who've seen the biology, I think biology did an elegant job because they said, you know, in biology there's 4 big ideas. And these are the 4 big ideas. Evolution, that has to do with the utilization of energy and the retrieval of information, and then how systems interact. Now, of course, this is a very high-level statement of these big ideas. There's a lot more underneath them, including a set of enduring understandings for each big idea. Essentially, for this one, the process of evolution drives the diversity and unity of life. There were a set of enduring understandings. And for any of you who are interested in this, it's not just at this high-level sketch. There's a long narrative that's associated with this, which is a very elegant description of what this means in terms of the big idea and the enduring understandings. And then there was a 3rd level as well, which is called the supporting understandings. And I'll get to that in a minute because that gets to the next part of the design process. But I want to say something that has not been talked a lot about in the AP redesign, not nearly at the level it should be, because I think it's very relevant to the issue of assessment and the design of assessment in AP and elsewhere. So if you look in the AP materials, you'll find 7 science practices. These science practices share similarities with what you find in other descriptions, like in the NRC framework. But the science practices, just like the core ideas or the content, were expressed at multiple levels. And we needed to do that for a variety of reasons, because you could sort of say, well, these are very high-level statements. What does that mean? Well, there was a 2nd level. So for this one, like work with scientific explanations and theories, there was a 2nd level that said that means these are different things that reflect a student's proficiency in doing that: justifying claims with evidence, constructing explanations, articulating the reasons that scientific explanations and theories are refined or replaced, make claims, and evaluate alternatives. The thing that you won't find, which is I think unfortunate in the materials for the AP, is you won't find the 3rd level. And the 3rd level is absolutely critical, because the 3rd level is about the observable data that are needed to support the claim that a student has actually achieved what's described at level 2. And this level of description, the evidence, is absolutely critical if we're going to think productively about assessment. Because remember what I said, assessment is reasoning, the process of reasoning from evidence. If we are not clear as we can be about the nature of that evidence, as related to both disciplinary core ideas and practices, we are going to have problems in terms of developing valid, reliable, and useful assessments. So this is an example of what I mean by evidence for this particular component of a practice. You don't have to go through the details, but the idea was in articulating the domain analysis, laid out the content, we laid out the practices, And that got us to the first phase of the redesign, the domain analysis. But if you're going to use evidence-centered design, you now have to ask, okay, we have to develop what's called the domain model. The domain model is a way to express what claims do you want to make about the student at the end of the AP course with respect to what it is that they know and can do, given the domain analysis in terms of the content and the practices. And so here you get into now stating the domain model in terms of claims. Claims, evidence, and we won't talk about achievement level descriptions for now. And what do I mean by that? So basically, what the domain experts did with a lot of help was to construct learning objectives which were the integration of aspects of the content with aspects of the practices, and created what in the AP are called learning objectives. That is, here's an example. The student is able to evaluate evidence provided by a data set in conjunction with a phylogenetic tree or simple cladogram to determine evolutionary history and speciation. This looks familiar in the sense of claims. These learning objectives are no different in some respects than the performance expectations you find in the next generation science standards. They are a statement about bringing together core knowledge and practices in terms of something that the student should know and be able to do, and it is that which is the demonstration of proficiency. Okay, that gets us partway there. So what we have is a domain model with claims and supporting evidence, and that now allows us to bring some coherence to AP courses and exams, in the sense that, first of all, it allows us to generate a curriculum framework. That curriculum framework, there's one in biology, there's one in chemistry, and there's one in physics. And I think an interesting point about the curriculum framework was that the AP program realized that in order for teachers to be able to teach to the new AP, they needed to have the curriculum framework at least 2 years in advance of when students were going to be tested, and certainly 1 year in advance before they were actually supposed to teach to that curriculum. So biology was, although the curriculum framework was for the year 2012-2013, because the first new biology exam was in the spring of 2013, the curriculum framework was released in 2010, so that teachers could get support and start thinking about this. And in the structure of the AP Biology curriculum framework, as I said, there's 4 big ideas. There's enduring understandings, there's essential knowledge combined with science practices to produce a set of learning objectives. That is what is in each of the new curriculum frameworks. The disciplines differ by how many big ideas they wanted or needed or felt they needed. How many physicists are there in the room? Okay, I'm going to mildly insult you. So the biologists were truly wonderful. You were involved in some of that. They said, we can do it in 4 big ideas. The chemists wanted more than 4. I think they had 5, maybe 6. The physicists wanted 14. He said, no, you can only have 7. I think they made it work with 7. The point was that to try to distill this down into not the whole discipline of physics, not the whole discipline of biology, but the discipline of biology for purposes of an AP exam that was going to promote deep understanding and support the other goals for the AP program. Of course, now, if you've got this and you can use it to drive this as well as instructional resources, you've got an assessment framework. You've got a way, because now what's in the domain model, the claims, constitute the targets for designing the assessment. Now we can talk a lot about the design of the AP assessment. I'll have some comments to make about that. I just want to sort of say a few things about that because I don't want to get too hung up on that. You can ask me lots of questions about it or make complaints about it later. I'm perfectly willing to take complaints because I have to say that my involvement stopped once they started writing the exam. So I'm not completely to blame for the exam. But I think it produced a number of changes in the biology exam, one of which is how they thought about the items, how they wrote the items, but they also have to tell you they struggled to get the Educational Testing Service to be able to write items that integrated practices and parts of core ideas. This was not something that typical assessment developers do easily or do well. Okay, and I'm not convinced they have yet done it as well as we would like. But the idea is that whether it's a constructed response or a selected response, students are going to either produce the evidence or engage with the evidence and reason about it rather than just retrieve factual knowledge. A couple of other changes. When you define the big ideas in biology, one of the things is a change. If essentially evolution is a big idea, the representation of evolution on the exam, you could track the difference between what was on there in 2028 and then 2013. Because of the emphasis on the practices and mathematical skills, new kinds of questions were developed. Okay, instead of just picking a number, you had to actually calculate. And then how do we do that? They used they used grid-ins. They used things that made it, still required the students to produce it, but made the scoring possible. Because of the use of evidence, they were able to reduce the number of multiple choice questions and increase the number of constructed response questions that caused students to engage. Now, some of us would argue they didn't go far enough, and that's because they designed the exam under a set of constraints that some of us would like to see change. One, paper and pencil, sit down 3 hours, and we could think of, if you freed up some of those constraints, you could do a better job. But on the other hand, it is still a work in progress. One interesting fact was when the first AP exam, biology exam, was given in 2013, as opposed to the old distribution of scores on the AP of how many 1s, 2s, 3s, 4s, and 5s, a lot of the 5s went away, not as many 4s, a lot more 3s, some 2s, and not that many 1s. And they've now administered biology 3 times, and it's not like you have a lot more 4s and 5s. So what they're recognizing is a very interesting thing at the College Board. They're not abandoning because now they believe they know what a 5 is and a 4 is because they've got a description of what a student knows and can do. They've said, you know what? It's not that these kids are not any less talented than the kids who used to get 4s and 5s before. We have to work with teachers and support instruction. Okay? We got to get help to teachers so that they can help the students to reach their potential, because it's not a problem of the test per se. It is a problem. We have to get much more involved in instruction. So what did we learn from the AP design project? This is really, really hard work. Okay, and it's hard work because to do backwards design and to do evidence-centered design, it requires a sustained process in execution. It requires multidisciplinary teams. It requires a lot of sustained effort in negotiation, and it requires time, money, and patience. I was at meetings where the biologists would argue about the big ideas and the enduring understandings, and it was like Survivor. I saw things voted off the island. And it requires people to engage in what I might call deep arguments about what's important and then how to express that. The value added is, from the point of view of an assessment, part of the arguments about validity, I would argue, is designed in from the start as opposed to grafted on after the fact. And because what you've got is what we call evidence of the validity argument are already contained in the process and the products. So that's a sort of quick sort of tour of the AP Science Redesign. I use it as an example of how you go from almost the start all the way through to an assessment. One of the interesting things, though, about the AP program is that historically it's just been an exam. with a very weak curriculum framework. But now the exam is part of an integrated model which is trying to drive science practice. We could talk about all the changes that have occurred in biology, chemistry, and physics classrooms, or not, as a result of the implementation of the curriculum framework and the exam. But I want to turn quickly to this project, to the K-12 world. I want to go back to the issue that faces now in K-12 as a way of sort of saying where we have to go. So most of you know that the NGSS is the product of a group of states with Achieve, following the ideas in the framework. It's built on the ideas of progressions in the sophistication of student understanding, and it includes, I think the most important and interesting part, is a new architecture with this focus on performance expectations. Many of you, I'm sure, have seen that architecture. It's standards like we have never seen them expressed before. The performance expectations for like 4th grade life science include things like construct an argument that plants and animals have internal and external structures that function to support survival, growth, behavior, and reproduction. There's clarification statements, there are assessment boundaries. This is what states that have adopted NGSS in whatever form they're calling it. I think Michigan has its own version of NGSS now. It's the Michigan Science Standards with a few tweaks, but it's still NGSS. This architecture poses a set of challenges now, because now the question is, what does it mean to meet those performance expectations, or how do we instruct and how do we assess against it? So there's some pluses and minuses of relying on performance expectations. On the plus side, it avoids the problems that we've had with prior standards, where we oftentimes express standards in terms of verbs such as know and understand. And I love that, although I'm a cognitive psychologist at heart, and know and understand are two of my favorite words. They're terrible when it comes to standards and assessment, because we don't know what it means to understand, and we don't understand what it means to know. And so the virtue of the performance expectations is they're stated at claims about students in terms of what they're supposed to know and be able to do to demonstrate their knowledge and they identify progressions. The downside is they don't tell us how to get there. Okay? They don't give us, they give us some clues, they give us some sequences, but they don't tell us how to get there in terms of curriculum materials and instructional practices. And as many of you in this room know, they need to be unpacked in terms of the forms of evidence needed to support the student claim. And this is the struggle right now. This is the struggle that teachers are facing. This is the struggle that states are facing as we think towards this. Now, a committee of the NRC was tasked with, so how do we solve this problem? I don't think we solved the problem. We identified the problems. We suggested some solutions. And one of the things that we said is that if you are going to support the vision of three-dimensional science learning, and you're going to have an assessment, you have to have three components in that system. You can't just build the large-scale test. You can't just build the monitoring assessment. You need to also build and support teacher practice and classroom assessment. We need to need to recognize the failure of the Common Core and the race to the top, which was we went from standards to building the big test, and we forgot about the classroom practice in between. That in essence, you have to have this and this have to complement each other, but you also need something else. If you're going to use assessments to make judgments about student performance and progress or teacher efficacy, etc., you need to have other information like indicators of opportunity to learn. Because if you don't have that information, you cannot make sense of the results of the assessment, particularly for policy purposes. Now, one other thing the NRC report said was give precedence to classroom assessments. Let's do for science what we didn't do for math and ELA. Let's build the assessments from the inside out. Let's start by working with teachers in classrooms to figure out what it means to build assessments that support teaching and learning and build from the inside out or the bottom up to the monitoring assessment. We're not going to ignore that. Now, that's a hard thing for states to buy. We can talk about balancing it, but the point we're trying to make is to get states to realize they need balanced assessment systems. They need to invest in two places. They need to invest in a high-quality monitoring assessment. They need to invest in high-quality assessment for teacher classroom use. So that brings me to the project Joe and I and other people in this room, Chris Harris and folks at SRI and Dan Daimler at the Concord Consortium are working on, supported by NSF. And I'm going to just sort of, so these projects are really trying to take up the gauntlet of what the NRC report said and to develop, using a systematic design approach, design tasks aligned with the PEs from the next generation science standards, develop and test technology-based tools and items, but also to do this in a way that supports teachers so that they can use these assessments formatively and to serve diagnostic purposes. We're not interested in building the large test. We're interested in building resources that support teacher practice. And we have a design model that we have worked through. What has it taken us, Joe? 2.5 years to figure this one out. It has 3 components to it, and I'm going to focus on one of them briefly. First is what we call unpacking, that is taking clusters of PEs, figuring out what the entailments are with respect to practice, core ideas, and cross-cutting concepts, creating what we call concept maps, and then the assessment argument. And I want to just spend a minute on that because I think this is very important in terms of thinking about the design of assessment regardless of what kind of assessment you're designing. So our assessment argument structure has these 3 components. The first is what we start with is the claims we want to be able to make about what students know and can do. What we construct what we call learning performances, and I'll say a little bit about what they are and how they relate to performance expectations in a minute. The second thing we ask is, what kinds of evidence will students need to provide to demonstrate proficiency? And then we ask, what task features can give us that evidence? And when we have that, and when we have those things in a coherent way, we can then start thinking about developing actual assessment items. And why do we use LPs? What are LPs? Oh, well, in a nutshell, learning performances are integrations of parts of the core idea and parts of the practices as implied by the performance expectations, but at a grain size that is smaller in scale, and it is something that might be part of the instructional path that a teacher might lead a student on to attaining the performance expectation. One of the confusions right now is teachers look at performance expectations and go, oh my God, what am I going to do with that? It's a very big expectation. How do I get there instructionally? What assessment can I do? Our goal is to design assessments that are tied to coherent, integrated combinations of practices and content ideas at a small enough grain size that it is connected to the performance expectation, but that it also can be used formatively, potentially, by teachers in classroom as they go along in instruction. I'll just give you one quick example of an item that comes from this design methodology, and I put this up there with great trepidation. There's no science assessment item I've ever put in front of an audience that doesn't get ripped apart in about 30 seconds or something, but we can come back there. Here's an example of Stephen found 4 different bottles filled with unknown liquids. He measured the properties. The measurements are displayed in the table. He wonders if any of the liquids are the same substance. Use the data in the table to write a claim stating whether any of the liquids are the same, provide at least 2 pieces of evidence, and then provide reasons to justify that. Now, how do we explain this item and its genesis? Well, we would say it's connected to this bigger performance expectation. Analyze and interpret data on the properties of substances before and after the substances interact to determine if a chemical reaction has occurred. Now, obviously, the item is not doing all of that. It's doing this. And it's doing this learning performance. Students should be able to construct an explanation about how they determine that substances are the same based upon characteristic properties. Learning performances are elements, and we have sets of learning performances that are related to each other and related to the larger performance expectations. What are the characteristic task features? Well, focus on density and boiling point. The tasks have to provide data about characteristic properties, and they have to provide a motivating context. What's variable? The number of properties to be included. Here we chose 2. The state of the matter, the inclusion of irrelevant data. Here we included irrelevant data, but you could not have that in there, or you could modify that. You can begin to look at this as ways to think about the features as a principled way to verify or to vary task difficulty and the demands on the students in terms of some progression of learning. And of course, we put in a level of scaffolding, which is, okay, we said to the student, give me a claim, give me 2 pieces of evidence, tell me how that evidence works. Now, at some point, you might sort of say to the student, essentially, give me an argument about whether anything is the same or different, and they would have to know they need to have a claim, evidence, and reasoning. So, if you want to see more about this, I'm proselytizing. Go to our website. You can actually see more items there. You can see our design methodology and the logic. The point of this is that, to go back to here, there are examples of trying to work this stuff through, and of course this is not a simple matter. Neither the AP work, even as far along as it is, or the work that we're doing and others are doing, only begins to get us thinking about what it means to develop quality assessment and have it integrated with curriculum and instruction. So, this may be the understatement of the year. We're all struggling with this because I think, and I saw it in various projects and posters, we need to translate the standards into effective models and methods and materials. And this means the things I saw on posters and a lot of us are doing, unpacking and clarifying the performance expectations, creating claims and evidence statements that are reasonable for teachers and students to try to attain and for assessments to be aligned to. We could have a long conversation about alignment of assessment, and we need to develop good task models and good task templates doing evidence-centered design. We also need to use what we know already to evaluate and improve a variety of other assessments that are part of current practice. One of the things that we talked about, I think it was at breakfast this morning or at dinner last night, was teachers need to understand what makes for good assessment and not so good assessment. And the way they need to do that is they need to look at the kinds of assessments they've been using, and we have to juxtapose them with the kind we want so that they can figure out why the assessments they've been using are not assessments of three-dimensional learning. They cannot learn and figure this out in the absence of good examples in contrasting cases. Will we have assessments worth teaching with and to? I'd like to believe we can, but sometimes what we in the R&D community and the practice community can do conflicts with the needs of the policy community and the needs of the federal government and things like that. So we need to, some of us are working very hard to get the federal government, including the federal funding agencies, to do the right thing and to help states do the right thing, which is not a simple matter because you're trying to influence policy under things like ESSA. Remember, frameworks and standards are the beginning, not the end. They're not a substitute for the hard thinking and the research that we need to do to define progressions of learning that can serve as the basis for curriculum instruction and assessment. Now, I haven't said much about higher ed. I put this up there because I know what you folks are trying to do, okay? How many of you authors are in the room here? This is not an easy thing to do, but what you're trying to do is very consonant with the ideas in the AP Redesign and the NRC framework. And, you know, changes in STEM education, higher education don't come easy. Sometimes when I talk to faculty, I sort of say, okay, what if you just did this? Think about the big ideas in your course, okay? what claims are you trying to make, or would you make about student knowledge and competence, or would you like to make as a result of students taking your course, and what are your assessments assessing? You can ask it at a higher level. It's a little more difficult, because now you're talking about multiple faculty, multiple courses and programs of study, and now you have to deal with all the personalities and vagaries of faculty and higher education departments and course sequences. But it's worth asking, because it's like saying, I will ask in my own department, what do I expect a psychology major to know and be able to do at the end of taking all of our courses, and where do these things fit in? And then, given the assessments and data that we have now, what claims can they support? What's missing? What should be changed? And I would sort of say that evidence-centered design, you know, even in a simple form, can be used in two ways. One, obviously, you can design new stuff, like AP and like we're trying to do with NGSS, but you can also use it in a backwards fashion. You can reverse engineer. I think your AAU project, in which you're actually doing some of that, or you're thinking about that, you're not actually reverse engineering, but you're actually trying to evaluate assessments in terms of the claims that can be supported and whether they're three-dimensional. And if you find ones that are good approximations, you can re-engineer them and build better ones. So you don't have to throw everything out. Maybe you have to throw a lot out, but how do you re-engineer it? The last thing I'd say is, assessment, as important as it is, should not be the tail that wags the education dog. Remember that assessment is part of a coordinated system, okay? And so long as it is coherent with and adds to the whole system of curriculum instruction and assessment, then we will start to make progress. The problem is going to occur when assessment drives the whole thing, and drives it in ways that are undesirable, and that's oftentimes the case with the state test. Thank you.
Thank you, Jim. We have about 10 to 15 minutes for some questions, and then we'll go on to our next poster session. So do you have questions for Jim?
There's got to be at least one question, a critique of at least one item. Go ahead. Yeah.
So you talked a lot about creating assessments and 3D for classroom teachers, and then for professors to look at the way they teach. Is there any kind of coordinated effort in terms of pre-service teaching programs? Or is that, that have to do with methods or assessments, right? Pre-service teachers take those classes? Or is it for individual professors or methods instructors to be thinking about that? Is it?
You asked about what I would call maybe the hardest nut to crack, which is how you change teacher education. And I don't know of coordinated efforts right now to try to change teacher education, but the way I think we need to think about this is as we prepare teachers to teach science, whether it's in the methods courses or wherever we do it, one of the things I've always felt is that issues of assessment and ways to think about assessment as part of teacher practice needs to be in the methods course, not in an assessment course. Okay, the typical assessment course does not focus on, it focuses on a range of issues related to assessment, but oftentimes not related to actual teacher practice. And my belief is that the way we need to get teachers thinking about this in terms of assessment is as an integrated part of their instructional practice. And to not get them hung up, and this is both pre-service and in-service, as, oh, this is more testing. This is not. It is about instruction and making students' thinking visible and acting on that and helping them understand what constitutes quality assessment, but also how to act on that in terms of implementing processes of what we call practices of formative assessment, because there is no such thing as a formative assessment in and of itself. It's all about how the information gets used. So I'm not sure how we make the kind of change. I mean, I was talking to Bob Floden this morning, and here in Michigan, you have 30 institutions that prepare teachers. I mean, now think of 50 states and all of the institutions. So it's very hard to produce coherence in teacher education because it is so, it is in so many different places with so many different groups of people running it that, on the other hand, I think the extent to which we get the ideas of the framework and NGSS and the kinds of what classroom practice has to look like in terms of instruction, assessment naturally drops into that because, in fact, you're talking about opportunities for students to provide evidence of how they're understanding. But I think it's really getting those who are in pre-service teacher education to talk with folks in assessment who think about assessment as evidence-based reasoning and not measurement, not just measurement. It's a long answer to your question because it's a big problem to solve.
I'm a high school science teacher and we're trying to get started with NGSS. You mentioned multidisciplinary teams. I was wondering if you meant that in the narrow sense of biology, chemistry, earth science, or if you mean pulling in math, language arts. What were your teams like?
So when we were in the work that we're doing, I would use our group as one example of a multidisciplinary team. We have science educators, we have assessment specialists, we have measurement folks, we have technology specialists, we have, to do this kind of work requires, we argue a lot. Okay?
It's a practice.
It's a practice, yes, right. but it's arguments about important stuff that matters to Joe with respect to the dimension, the 3 dimensions, stuff that matters to me about okay, what does that mean in terms of evidence? So that's one form of multidisciplinary team, and I think that comes in the R&D world. In your world, I think there is the need for multidisciplinary teams because if you look at the standards, ELA, math, and science, they have connections to each other. And in fact, it would be very beneficial if we could get that kind of crosstalk with respect to even good discussions going about evidence and argumentation as students grapple with text, and whether they're reading historical text, literary text, or scientific text. Because quite frankly, the ELA standards talk about the different disciplinary areas and they talk about argument and evidence, but students need to understand what constitutes evidence for historical argument and how that's similar to and different scientific evidence for a scientific argument, and the same for literary argument. This is the area my wife works in, and she, and this is a really important thing. And then you can also think about the natural connections between math and science with respect to many of the activities. So our tendency is to sort of say, is to keep them separate. Social studies should be there too, because social studies and history has some of these exact same issues. So I think it depends on what level you're at. I also think it wouldn't hurt if the chemistry folks talk to the biology folks who talk to the physics folks. and have some interesting discussions about how do you use models versus how do I use models. That was when we were doing the AP redesign, I should just mention it, I listed those practices there, but the practices then have to get instantiated in terms of what kind of models do biologists use, what kind of models and representations do chemists use, do physicists use, and then how do they use those as essential in part of their work. And so we tend to sort of say it's all science. Well, it isn't.
In reference to the first question, I want to make a uneducated plug for NGSX.
Yes.
It is. Do you know a bit about that?
I know about it because it's Brian.
It's just made its way here to Michigan and is being offered through the ISDs. It involves teachers in 5, 6, or 7 full-day sessions, helps them unpack the standards and begin having conversations about what we're looking for in evidence-based learning.
NGSX has been part of a project that we're involved with the Illinois State Board of Education as well, with teachers in Chicago and CPS. And I think it does a good job of getting teachers into this. What we've discovered is they still need, it doesn't get you all the way to thinking about assessment.
Right.
Okay? But it's a natural way. We just did a PD with all the NGSX to tease, so to speak, about assessment and evidence, because it sets up a very natural way to think about evidence in the classroom and to open the conversation about quality assessment. So, and
You're on the right track?
I think it's on the right track. I mean, yeah, Brian was part of the framework, and I think what he's trying to do with NGSX is to advance that vision.
So, do you have any idea how students performed on that one question that you showed? How distinguishing the different, whether substances were different from each other?
Well, we've got a little bit of field data, but we're actually at the point of a lot of our items that we've designed. We're trying to collect large amounts of performance data to look at the range of the responses that we get from students. One of the difficulties we have to have, and this is a real challenge, is how do you validate these assessments if kids have not been instructed in ways that engage us? So we have to find classrooms that are in some ways engaged in NGSS or framework type assessments, so it's legitimate for us to put that down. And we work with teachers to sort of say, is this a good question that you could ask your kids because of the instruction you've been doing? Then we can look at the student performance, because otherwise the odds are that students are not going to do very well, they're not going to give you any information, and then you don't know whether the assessment item is not any good or whether it's just simply a floor effect. So tune in, ask Joe in about 6 months, we'll have some answers to that question.
Other questions? Yeah, way in the back. Speak hard. Well,
Oh, I will. Thank you for your presentation. One question that I have, and I'm seeing this in various presentations now across the U.S. One thing I noticed in your presentation is that you really seem to focus on disciplinary core ideas and practices. I see a little bit of absence of the cross-cutting concepts. In other presentations I've seen in other research, they're focusing on the cross-cutting concepts as being the backbone of curriculum and instruction and even assessment, and sometimes tend to leave out the practices. So I'm getting this like three's a crowd type of feeling, and wondering how we as educators, as curriculum and instructors, as assessment designers, how we can make sure we're giving fair time and fair access to all three dimensions, and making sure that those things are teased apart.
Okay. So in the AP work, it predated the framework, so it was just you might call content and practices, and it was discipline by discipline, and so there wasn't a deep discussion of cross-cutting concepts. But I understand exactly where you're coming from. When we first started working on the design of our items, we sort of pushed the cross-cutting concepts to the background. And then we sort of brought them back in again in terms of the specification of the learning performances. But I would argue that the cross-cutting concepts are really important when you think about continuity of instruction over time and developing those understandings. But the cross-cutting concepts are very hard to sort of identify and separate out specific aspects of it to make it easy to sort of say what's evidence of the cross-cutting concept. So there may be a difference in the sort of say the extent to which you really get in teachers' minds and in the design of curriculum and instruction an emphasis that makes sure that the cross-cutting concepts are reflected and you keep coming back to them, and that you do sort of think about them in the design of the situations you're creating. But I would argue, and others might want to disagree with me, that for purposes of designing reasonable performances where you're trying to get evidence about what kids can bring together, the disciplinary core ideas and the practices are, fit together well, and the cross-cutting concepts need to then be there as a guide to sort of saying, okay, are we looking at cause and effect here? Are we looking, but are you, and maybe you can get at some of that, but I think it's hard to do all three things simultaneously. If I were to lay bets or odds, I would sort of say it's integration of the core ideas and the practices, and the cross-cutting concepts need to be there, but they need to be there, what I would call on a larger longitudinal, thinking about it, rather than a single episode. Because I don't think, if you think about the cross-cutting concepts, they are big ideas of a different sort that get built up across multiple PEs, multiple dimensions of science. And so we got to bring them forward in people's minds, but it's hard to figure out how you actually directly sort of, quote, measure them, although I hate to think about just trying to think about that.
This might be one of those areas that Jim said we would argue about. Anyways, let's give Jim a big applause. Jim will be around to talk about that. Thank you, Jim. A lot of stuff to think about in the go forward. I want to remind everybody that we're not done yet. We still have a whole other poster session to go to. There's plenty of food to keep you going. So there's good food, good conversation, and great posters still to be there. So thank you, everybody.